This lesson is on simple harmonic motion and its relation to circular motion, and here are your objectives. First, let's recall from our discussion of circular motion that angular speed, which we give the symbol omega to, means the time rate of change of angle, how quickly you're sweeping out an angle as you go around in a circle. And because a full circle is 2 pi radians, that is, if you start from here and you rotate all the way around, you have traveled through 2 pi radians, then something that is rotating at constant speed is going to go through that 2 pi radians in one period of time, one period being by definition the time required to complete one cycle. So angular speed is equal to 2 pi radians divided by the period, and because period is equal to 1 over the frequency, we can rewrite that as 2 pi times the frequency as well. So again, angular speed is in radians per second and is telling us how quickly we're rotating through an angle. So why am I talking about this now when we are interested in simple harmonic motion? We'll take a look at this animation. I'll put the URL for this page in the video. We see an object undergoing simple harmonic motion from left to right. Now I'm going to put a line there so that you can see it going back and forth. This is simple harmonic motion, but watch this. It's also a side view of an object going around in a circle at constant speed. There's our object going around in a circle at constant speed, and there we are looking at it from the side, and we get simple harmonic motion. So there's this connection between simple harmonic motion and a projection of an object going around in a circle, as if we're looking at it from the side. And so if we can find a way of expressing the coordinates of something going around in a circle, we'll also be able to use that for simple harmonic motion. So using a bit of trigonometry, remember that if we have an object going around a circle, if the circle is of radius a, and this is the angle theta, then the projection onto the horizontal axis, in other words, its x-coordinate, is going to be a cos theta. In other words, the position in the x dimension of this point here, x as a function of time, is going to be a times cos theta. But what is theta as a function of time? Well, recalling that we said up here that the angular speed omega is equal to the time rate of change of the angle, if we start from an angle of 0 over here and a time of 0, then this becomes just theta over t, and therefore theta becomes omega, the angular speed, times time, again because we've started from 0. And so x as a function of time is equal to a times cos of the angular speed times the time. And so now we have a relationship between the angular speed of this object going around the reference circle and the projection on the side view, which is tracing out simple harmonic motion. And so we're going to use this quantity omega, which we called angular speed. We can now also call angular frequency, because it's related to the frequency of this object oscillating with simple harmonic motion. We're going to use this quantity omega going forward as we talk about simple harmonic motion. So what we've just developed, therefore, is an equation for the position as a function of time. So the position as a function of time is equal to the amplitude, that gave us the radius of our reference circle, times the cosine of the angular frequency times the time. And also remember that this angular frequency or angular speed is equal to 2 pi over the period, so we could replace it with that. Now in this case, we were looking at the x-coordinate of the reference circle, and we started from a position of maximum displacement. We started from right here. We could also have started from the equilibrium position, and if we start from the equilibrium position, in other words, if we started from when the object on the reference circle was right there, we need something that starts off at a 0 and still traces out a sinusoidal shape. And so we need a sine curve. And so an equivalent equation, or an alternate equation, is sine of omega t. And we're going to use these in two different cases. We're going to use this one when we start at an extreme of motion. So when we start at one of the ends. And we're going to use this one when we start at the equilibrium position. And they would be interchangeable if we introduced a horizontal translation in here, but just changing the function simplifies that. So let's just go back and make sure that the connection is clear once more. We've got this object oscillating backwards and forwards, and its equilibrium position would be right there. And so this distance, that distance there, is the amplitude A of its oscillation. And if we look at the reference circle, that becomes the radius of the reference circle. And it's going backwards and forwards with an angular frequency of omega. This quantity is easiest to think about when you start to picture the reference circle that's underlying this. So think of the simple harmonic motion and then imagine it as the projection on the side, or the side view of an object going around in a circle. That quantity, the angular frequency, is describing the constant angular speed that the object on the reference circle is going around with. And then we've just derived some equations, two different equations depending on whether we start here at an extreme, in which case we'd use the cosine function, or if we start at time 0 here at the equilibrium, we would use the sine function. Let's do one more thing and take a look at how we can connect this quantity angular frequency to our equation for the period of a mass on a spring. Remember that our period for a mass on a spring was equal to 2 pi times the square root of the mass divided by the spring constant. Now, if we rearrange this a bit, let's divide both sides by t, the period, and then divide both sides by this square root sign. So if we do that algebraically, we end up with 2 pi divided by t, and then the square root of k over m. Again, I've divided both sides by t and then divided both sides by this, so I had to flip the fraction. Well, we've said that this is our omega, our angular speed, our angular frequency. And therefore, we now have the relationship that the angular frequency is equal to the square root of k over m. Be careful, this is upside down from what we see in the period equation. And if we square both sides, we get omega squared is equal to k over m, and that's a relationship that we'll find useful going forward between the angular frequency, the spring constant, and the mass for an object oscillating on a spring with simple harmonic motion. So what we've seen in this lesson is that if we think about simple harmonic motion in terms of underlying circular motion, we get powerful tools for describing that motion mathematically.